Now I think I've taken the general case as far as I can. We can't do anything until we know what K and M are. And so now I'll introduce what's actually the first example of this set of videos here. A mass weighing 32 pounds stretches a spring 2 feet. Determine the amplitude and period of motion if the mass is initially released from a point 1 foot above the equilibrium position with an upward velocity of 2 feet per second. And then we're going to look at how many complete cycles the mass will have completed after 4 pi seconds. Some things to unpack here. Number one, a mass weighing 32 pounds. The mass weighs 32 pounds. 32 pounds is not mass. Pounds is force. This is the imperial system. It's, pounds, feet, inches, all that stuff. If we were looking at the metric system, then kilograms is going to be mass. And mass times acceleration is force. Newtons is equal to kilograms times 9.8 meters per second squared for gravity. That is force. Here, pounds is force. And again, mass times acceleration. Acceleration due to gravity in the foot-pound system is 32 feet per second squared. I'm not writing the units. And so the mass, we end up dividing, right? So 32 pounds divided by 32 feet per second squared is going to be 1. What are the units? Slug. Okay, so units of mass in the system that we use mostly in the United States is slugs. What we get from this, m is equal to 1. Now, we also have that mass that has a force 32 pounds stretches the spring 2 feet. The force is 32, K is what we're finding, and S is 2. Therefore, in this case, we have that K is equal to 16. And in case you're wondering, it's pounds per foot, but that's not something I'm really going to ask you to report to me. So we've got, in our case, as we just said, m is equal to 1, K is equal to 16, and so omega squared is 16 over 1, which means that omega in this case is equal to 4. So our equation of motion is x of t is equal to c1 cosine of 4t plus c2 sine of 4t. Based on this, we can immediately find the period. You may remember from graphing trigonometric functions that the period is, for a sine and cosine, 2 pi over omega, omega being the coefficient of the variable inside the trig function. And so in this case, it's 2 pi over 4 or pi over 2, and the period's going to be in seconds. If you ever need it, the frequency is 1 over the period. And so in this case, it would be 2 over pi. And the frequency is in hertz. I'll just say hertz. It's cycles per second. Well, look, if we've got 2 over pi cycles per second times 4 pi seconds, which we just saw we were going to be asked to answer about, that's going to give us 8 cycles after 4 pi seconds. All right, so we've got the period, we've got the cycles. That was the easy part. If you look back at the instructions, we were also asked for the amplitude. We also have some information in the form of initial conditions. The masses are initially released from a point 1 foot above the equilibrium position. That means that the position, x at 0 seconds, is equal to, and then 1 foot above equilibrium, remember down's positive, so this is going to be -1, with an upward velocity of 2 feet per second. That's going to give us that x prime of 0, initial upward velocity, upward negative, so -2. Let's incorporate that information here. So we've got our equation of motion here. If t is 0, the sine function zeroes out. And then we have the cosine of 0, which is 1, times c1 is equal to negative 1. That gives us c1 is negative 1. Then we have that x prime of 0 is equal to negative 2. Some folks will go back to this equation here that has the c1 and the c2 sine and cosine and work from there. We already know that c1 is negative 1. So first, before I differentiate anything, I'm going to write down that x of t is equal to negative cosine of 4t plus c2 times the sine of 4t. And at this point, it's c2 that we're trying to find, right? X prime of t is then equal to, I almost wrote negative, 4 times the sine of 4t plus 4c2 times the cosine of 4t. X prime of 0 is going to zero out the sine term and give us 4c2 is equal to negative 2, which then means that c2 is negative 1/2. So using that, we have the equation of motion with the constants nailed down. X of t is equal to negative cosine of 4t minus 1/2 sine of 4t. And you may notice this is a little tough to look at and determine the amplitude. It'd be a lot easier if it was sine or cosine. It's a little harder when it's sine and cosine. For what we need to do, we're going to get into some trig. So we're going to take a sidebar here, and we're going to go back to the form where we had x of t was c1 cosine of 4t plus c2 sine of 4t. Suppose we create a right triangle, and the right triangle has its vertical side c1, its horizontal side c2, and the bottom acute angle we're going to call phi. The hypotenuse, as you know, is c1 squared plus c2 squared. As far as phi is concerned, the sine of phi is c1 over the hypotenuse, c1 squared plus c2 squared. The cosine of phi is c2 over that hypotenuse, c1 squared plus c2 squared, in a square root, of course. And the tangent of phi is equal to c1 over c2. If we take this equation, or this function x of t, and multiply and divide by that square root, then we have the square root of c1 squared plus c2 squared times c1 over the square root of c1 squared plus c2 squared times the cosine of 4t plus c2 over that same square root of c1 squared plus c2 squared times the sine of 4t. What we have then is the form of, well, look, c1 over the square root, we said was the sine of phi. So I'm going to pull this out of the function, and we're just going to focus on the trig part. What we have is a form of the sine of phi times the cosine of 4t plus the cosine of phi times the sine of 4t. And you may recognize this as an identity. It's actually a phase shift of a sine function. This actually is going to be the sine of 4t plus phi. So we can rewrite x of t as x of t is equal to the hypotenuse length, c1 squared plus c2 squared, times the sine of 4t plus phi. To find out what phi is, well, the tangent of phi is c1 over c2. What were c1 and c2 in our case? Well, we had that c1 was negative 1 and c2 was negative 1/2. So the tangent of phi, which is c1 over c2, is 2. But note, if c1 and c2 are both negative, right, the numerator, well, I guess the sine and the cosine are both negative, then that means that phi terminates in quadrant 3. So in radians, phi is going to be the inverse tangent of 2 plus pi, which is about 4.24. So x of t is equal to the square root of -1 squared plus -1/2 squared times the sine of 4t plus 4.24. That square root simplifies to the square root of 5 over 2. So we have that times our shifted sine function. And that's the equation of motion for the system. Further, that square root of c1 squared plus c2 squared is the amplitude. So the amplitude here is the square root of 5 over 2, which is approximately 1.118. I guess I can put feet. Now that answers the rest of the question there. If we wanted to see a visual of this, there is something we need to remember. And when we set all this up, we said down is positive. If we type this into like a Desmos, which I've actually done here, we're going to see that this is not right for the situation. You can see that it crosses the y-axis down there at -1. But we were told it was released above equilibrium. So we have to actually multiply it by a negative. And when we do that, we have this graph of a mass that is released at 1 unit above equilibrium, and its first motion is to go up. And that would be due to the upward velocity of 2 feet per second. So this thing, it's going to be launched up, and then it just starts oscillating up and down and up and down with an amplitude, a maximum distance from equilibrium of about 1.118 feet. Let's recap what we did with the trig here. For x of t equals c1 cosine omega t plus c2 sine omega t, the amplitude is going to be basically the hypotenuse of an associated right triangle. So the square root of c1 squared plus c2 squared. C1 divided by that amplitude is the sine of an angle phi, and C2 divided by that amplitude is the cosine of an angle phi. A quick way to figure out what the angle is that the tangent of the angle phi is C1 over C2 sine over cosine. Then x of t turns out to be the square root of C1 squared plus C2 squared times the sine of omega t plus phi. On occasion, it's more desirable to express this in terms of a cosine instead of a sine. I would encourage you to review the sum formula for the cosine function to see why x of t would be equal to the square root of c1 squared plus c2 squared times the cosine of omega t minus phi. But in that case, the tangent of phi is going to be c2 over c1. You talked me into it. I'll give it to you quickly here. Remember that the difference formula for the cosine function is cosine of alpha minus phi equals cosine alpha cosine phi plus sine alpha sine phi. So to represent this as a cosine instead of a sine, when we used the sine, c1 was associated with the sine function. But now when we're using the cosine, c1 should be associated with the cosine of phi. That means c1 is down here in the horizontal side of our triangle, and that gives us that the tangent of phi is c2 over c1, and it's just a difference in the role that c1 is playing, whether we express the shifted function in terms of a sine or a cosine.